All right, everyone. This is our second lesson on our Earth and climate change unit. Here we're going to focus on the sun and how that affects Earth's climate systems. So we talk about the sun. We're not going to get into the sun in terms of astronomy. We're going to focus on its effect on the Earth a little bit. So of course, it's the source of our energy here on Earth. It's necessary for all plant growth. We talked about this in our biology unit, where plants get the energy they need for photosynthesis from the sun, and it's crucial to human survival as well. Not because we use the sun necessarily for energy or for food directly. Obviously, we use it as a means to produce plants, and then the animals that we eat those plants. But we also require the sun so that the Earth stays at a habitable temperature. Our Earth is in this what we call Goldilocks zone within our solar system, where the sun is the perfect distance away to ensure that human life is sustainable. It provides the entire planet with heat. So the average surface temperature of our planet is about 14 degrees Celsius or 287 degrees Kelvin. Kelvin is a unit of temperature that's common in a lot of science, chemistry, and physics. If you go on to take some more science, you'll see that unit of measurement there. So just in case you come across that at any point in your life, that's why I've included it that way. So of course, without any sun, plants on our Earth would not be able to grow. If the sun was too far away, all of our liquid water would be ice. If the sun was too close, or we were too close to the sun, we wouldn't have enough liquid water. It would all evaporate. That's 14 degrees Celsius there. That's a global average. Of course, as you get closer to the equator, we have areas that can get over 55 degrees Celsius. As you move away from the equator, down to the South Pole as an example, we can get down to almost negative 90 degrees Celsius. So there's a big range of temperatures on our Earth. But like we spoke about yesterday, the climate in those regions has adapted to those temperatures. So we see different vegetation at the equator than we do at the poles, for example. So the sun is our main source of energy. As we said, the Earth is in a very specific spot in the solar system, or in our solar system. There's a delicate energy balance that has to be maintained. So if we moved further away or closer to the sun, we would be in trouble. So if the energy absorbed on Earth by the sun was greater than the energy that the Earth gave off, then obviously our Earth would heat up, right? The energy coming in is more than the energy leaving, so there's a net leftover amount of energy which will be converted into heat, which will cause the temperatures on Earth to rise. If the opposite were to happen, so if we didn't take in as much energy as we gave off, obviously we would cool down. Okay, so what does this look like? In general, this is what the energy pattern or the energy flow from the sun to the Earth and then out again looks like. You can see here that if we assume that we absorb all the energy coming from the sun, obviously we don't. But 100% of the energy that does come in is eventually lost somehow. About 30% of the sun's thermal energy is reflected back immediately, so it hits the atmosphere and reflects back, or it hits the ozone layer and reflects out, reflects off water or other means. We'll talk about that a little bit more on the next slide. But the remaining 70% is either transmitted through particles and then absorbed, or just absorbed right away. And then that energy takes some time to dissipate back out of the Earth, back into space, for example. About 50% is absorbed by the land and the oceans. Water is a great, has a very high, what we're going to call heat capacity, so it has a very high propensity to absorb energy. So water can absorb a lot of energy without having to increase its own temperature. That 70% that leaves the Earth leaves in the form of low energy infrared radiation. So if you remember back to our optics unit, we talked about the different types of wavelengths of light and how we go from, let's say, radio waves all the way down to gamma rays, and how those all have a corresponding different amount of energy. So if we talk about specifically the energy that is absorbed, or the energy that's coming in, when that energy from the sun, which we're going to call thermal energy, reaches Earth, and it obviously bounces around, hits particles of matter, right? It's going to hit water mostly, or oxygen, any gases in the atmosphere. That energy can be absorbed by the particle, and that causes that particle to gain energy for a certain amount of time. This principle of gaining infrared energy is used a lot in chemistry when we're classifying chemicals. We have been able to identify how much a compound, whether it be, let's say, water or carbon dioxide, oxygen, nitrogen, how they react when they're bombarded with infrared radiation. And each of these molecules or atoms or compounds reacts a little bit differently. So they all absorb radiation at a slightly different wavelength. Some won't absorb any radiation at all, and that thermal energy will pass right through them. And then some others will have the thermal energy reflect off them. So again, like we said before, that was about 30% of the thermal energy that comes into Earth is just reflected right off. It's either reflected by the atmosphere or the clouds, which are mostly made up of water, or it's reflected by the surface, by what we're going to call surfaces that have a high albedo, which is a high propensity to reflect light or light energy. The light that gets transmitted through particles then has to either be absorbed by a particle or then reflected off by another one. So that's not it's not counted into that kind of, there's 30% that gets reflected and 70% that gets absorbed, because obviously if it's transmitted, it's not lost, it's going to end up in one of the other two forms. So the sun and Earth, they work together to kind of provide these climate systems. So the atmosphere is probably a term that you are familiar with. We're going to talk a little bit more, we're going to go into depth about the atmosphere in our next lesson, but the atmosphere is essentially made up of the gases that surround the Earth. We're going to talk about that makeup of gases in a little bit, or I guess in the next lesson. The hydrosphere, hydro meaning water, is a climate system that deals with, let's say, the water cycle, all forms of water, whether it's solid, ice, liquid water in the oceans, or water vapor in the atmosphere. The lithosphere is where we're going to talk about soil, rocks, sediment, any minerals that the Earth is made up of, and that can be on the surface. So soil on the surface of the Earth, or a mountain on the surface of the Earth, or soil, rocks, minerals found at the bottom of the ocean. And then obviously living things, that's you and I, plants, animals, how we breathe and how we interact with each other. So the last part of this lesson is just kind of taking a look at the climate zones. We spoke about climate zones very briefly in the last lesson. And the one thing we need to know is that the Earth is tilted. So the Earth is on an axis. It doesn't spin upright like a top, it spins a little bit crooked. And if we take a look at the area, so on figure A there, we can see that the energy from the sun is most intense near the equator, because those areas are hit directly by the sun. So we can see that almost all of the energy from the sun is hitting the same spot. So it's not exactly around the equator. Some parts will be above, some parts will be a little bit below. This energy from the sun is less intense near the poles, North Pole and South Pole, because it hits, the energy from the sun is hitting the earth at an angle and is being spread over a larger area. So the same amount of energy is coming in, but is being spread over a large area. Okay, so hopefully you can understand why that is causing more energy to be concentrated at near the equator and less energy to be concentrated near the poles. If you want to think of an analogy, right, we can think of if you step on one nail, there's a lot of pressure there, and you feel that, whereas if you step on a bed of nails or lay down on a bed of nails, the pressure is dispersed. So it seems like it's a little bit less. Okay, so again, that's it for this lesson. Hopefully you filled out the notes. If not, you can review this and ask me any questions when we get back to class.